In the previous video, we have seen that we may use the dual optimal solution to obtain shadow prices. So let's apply that to some examples. We are going to use the modified Dakota problem. In the next slide, you will see the Dakota problem, and I will pause the video to give you the time to read the problem and get the context of this problem. The only modification is that we are ignoring the constraint of the limitation of the table demand. So here are the 5 questions related to the Dakota problem. We are going to use the concept of shadow price and dual optimal solution to answer these 5 questions. So let's start. The first question asks us to obtain the shadow price for each constraint. We are given the optimal table to the Dakota problem. So here what we are going to do is that we are going to read this optimal table to obtain dual optimal solution. And then from that dual optimal solution, we will get the shadow price. Okay, so that's what we are going to do. So first we are going to read the optimal dual solution from the optimal table. And then we see that the primal problem is a max problem. So here are the guidelines. Okay. So we have 3 constraints here. It means that in the dual problem, we will have 3 dual variables, y1, y2, y3. And then the first constraint is less than or equal to, so we may just read the coefficient of S1, which is 0, and then the coefficient of S2, again, because this is less than or equal to, and then the third constraint less than or equal to, so we may just read the coefficient of S2 as the value of optimal dual solution y2, and then the coefficient of S3 as the value of the optimal dual solution y3. So the answer is 0, 10, 10 are the optimal dual solution for this problem. See that I have not talked about the shadow prices yet. From at this step, I have just obtained optimal dual solution, but not the shadow prices yet. Now remember that the relation between dual optimal solution and shadow prices, if the problem is maximization primal, looks like this. So the shadow price of the ith constraint is the same or equals with the optimal value of the ith dual variable. Well, that's good. So it means that the shadow price of lumber is 0, the shadow price of finishing is 10, the shadow price of carpentry is also 10. Now let's do kind of a further interpretation of each of these shadow prices. So for the first shadow price for lumber, the value is 0. It means that if we increase lumber by 1 unit, the change in Z value is 0. Why is this the case? Well, we may see that currently we don't consume all lumbers that we have. So we have 48 board feet of lumbers, but we only consume 24 of them, I believe. Because you see that we still have the slack S1 equals 24. It means that we are 24 below the availability of lumber constraints. So we don't consume all lumbers that we have. It means that why would we want to increase the lumber by 1 unit if we don't even consume all that we have at this moment? So it does make sense that adding lumber would not benefit Dakota at all. Therefore, the shadow price is 0. In other words, Dakota would not be willing to pay any money for additional amount of lumber. For the second constraint, finishing, we see that the shadow price equals 10. It means that if we increase finishing hour by 1 unit, the change in Z value is plus 10. In other words, the z-value is increasing by 10 units. And this is kind of making sense because currently we consume all finishing hours. We have 20 finishing hours and then we consume all of these finishing hours. You may see this from the fact that S2 is a non-basic variable, which means that S2 equals 0. In other words, we consume all these 20 finishing hours. So the shadow price 10 may mean that Dakota is willing to pay up to $10 for each additional finishing hour. Because by having one additional unit of finishing hour, the revenue or the Z value will be increased by 10. So Dakota is willing to pay up to $10 for each additional finishing hour. Similarly, for carpentry constraints, the shadow price is 10, and we may do the same analysis. It means that the Z value will be increased by 10, and then currently we consume all carpentry hours because S3 equals 0. It is a non-basic variable. And then the shadow price 10 in this case may mean that Dakota is willing to pay up to $10 for each additional carpentry hour. But then let me make a note that this is not always the case. Shadow price 10, then we are willing to pay up to 10. We are going to talk about this more detailed in the next video. Just keep this in mind that this is not always the case. You have to be kind of a bit careful, and we're going to talk about this in the next video. Now let's move on to the second question. Here it says that if 18 finishing hours were available, what would be Dakota's revenue? And then there's a note here saying that it can be shown by the methods of section 6.3. This is the section about the 6 changes in sensitivity analysis. That if 16 less than finishing hours less than 24, the current basis remains optimal. Okay, so 18 is still within this range, so the current basis remains optimal. We still may use this set of shadow prices. Okay, so the current finishing hours availability is 20 hours. And then now suppose we only have 18, what happens? Since we have obtained the shadow prices, including the one for finishing, we may just use this formula here for maximization. The new optimal Z value equals the old optimal Z value plus the change times the shadow price. So the old Z value for this Dakota problem, you may see this from the previous slide, is 280. And then the amount of change is minus 2 because currently in the original problem, the finishing hours is 20 hours. Now we change it to become 18, so minus 2. And then the constraint I shadow price, the shadow price of finishing is 10. So we get the new Z value equals 260 if we only have 18 finishing hours. So the third question is that if 9 carpentry hours were available, what would be Dakota's revenue? It may be shown that the carpentry hours between 6.67 up to 10, then the current basis remains optimal. It means that this 9 carpentry hours still keep our current basis optimal, so we may still use this set of shadow prices. Okay, same as before, because this is maximization problem, we may use this formula to obtain the new Z value using the change and the shadow price. So the old optimal Z value is 280, and then the amount of change is from 8 carpentry hours to become 9. It means we are adding 1 hour, so delta B equals 1. And then the shadow price for carpentry is 10, so the new Z value equals 290. Now, if 30 board feet of lumber were available, what would be Dakota's revenue? And then it may be seen that if the lumber availability is between 24 up to infinity, then the current basis remains optimal. Okay, so 30 still keep our current basis optimal. We may still use this set of shadow prices. Again, we're going to use this formula because this is maximization problem. We are going to use this formula to compute the new Z value. The old Z value is 280, and then the change in lumber is 18 because we moved down from 48 to 30. So this is minus 18. But then you see that the shadow price for lumber equals 0. It means that when we change the availability of lumber from 48 to 30, our optimal value does not change. And this again makes sense because remember that we do not consume all of this lumber. We only consume 24 board feet of lumber. If you go back and check the optimal table of this Dakota problem, you see that S1, the slack for the first variable, equals 24. It means that we only consume 24 board feet of lumber. So if the availability goes down from 48 to 30, it is still okay. It will not affect our current optimal solution or optimal basis because we only consume 24 board feet of lumber. So 30 is still more than enough for us. Now the fifth question says, if 30 carpentry hours were available, why couldn't the shadow price for the carpentry constraint be used to determine the new Z value? Well, if we look at the third question, it says that the carpentry hour must be between 20 over 3 up to 10 such that the current basis remains optimal. Remember, if the current basis remains optimal, then we may use this set of shadow price. 30 carpentry hours is clearly outside of this range. It means that the current basis is no longer optimal. We cannot use the current set of shadow prices. Then what should we do if we really would like to know what happens if we have 30 carpentry hours? Well, you may apply the change in right-hand side in one of the 6 cases in the sensitivity analysis. Apply the change in the right-hand side and from 8 up to 30. And then I think we are going to need dual simplex to solve the new problem after the change. And then we are going to talk about this dual simplex later next week. But that's the idea. If the current basis is not optimal anymore, it means that you need to resolve the problem, either by applying the sensitivity analysis, or you just change this value from 8 to 30 and solve the simplex algorithm from the very beginning. The point is you need to find the new optimal solution and obtain the new set of shadow prices. So here's a question to check your understanding. In a maximization problem, for example, the Dakota problem, for a constraint with less than or equal to sign, for example, lumber constraint, here's the statement. If we increase the right-hand side, then the new feasible region must be as large as or even larger than the original feasible region. Is this statement true or false? I will give you the pause on the video to give you the time to think, and then I will give you the answer after that. The answer is true. Suppose we are increasing the carpentry's right-hand side from 8 to 9. The original feasible points that use less than or equal to carpentry hours, or in other words, the original feasible points in this problem, they are still feasible. And in addition, we may have some new feasible points that use carpentry hours between 8 up to 9 hours, right? So adding carpentry constraint from 8 to 9 may add some new feasible point. I emphasize the word may because it may or it may not. But the point is the original feasible points that use less than or equal to 8 carpentry hours, they are still feasible. So the new feasible region must be as large as or even larger. The new feasible region cannot be smaller than the original one. The relation with shadow price is that if we know that the new feasible region after changing the right-hand side, after increasing the right-hand side, will never be less than or smaller than the original problem, it means that the shadow price of a constraint with less than or equal to sign in a primal maximization problem must always be non-negative, because increasing the right-hand side of such constraint will never decrease the z-value. This is the case because our feasible region after the increase must be as large as or even larger. If we have a feasible region that is the same or even larger, it means that our z-value in the maximization case must be at least the same or even larger. It cannot decrease because now you have more points in your feasible region, so it only makes sense that you have more options to get a better optimal point, right? So that's why the shadow price will never be non-negative. It means that increasing these kind of right-hand side in these constraints will never decrease z value. At least the z value is the same or it may even increase. Okay, so that's the end of this video. And then in the next one, as I've said before, I'm going to talk about why we need to be careful when we interpret shadow price. It is not always the price that we are willing to pay for an additional unit of resource. So see you in the next one. Thank you.